Anyway, we're doing this simple reaction, A to B, and we know uh, Gibbs free energy, function, temperature, pressure, and the mole numbers, and we have the chemical potential, which is the molar Gibbs free energy for A, given by this, and so it's some standard state RT log. The partial pressure divided by that standard state, so if PA was equal to P naught, I'll call that naught. It looks like something else, but that P over P naught, if P was equal to P naught, PA was equal to P naught, then mu A would be mu A naught. Same with B. If we take the difference of these, and this is a special case because the stoichiometries are 1 and -1, so it looks a little simpler than a more complicated and more realistic reaction. But that's our reaction Gibbs free energy is equal to the difference between these two chemical potentials, so it's equal to that. Or if we just do a little algebra and redefine the standard state reaction change in Gibbs free energy plus this term that depends on how far we are from the standard state. We're not at the standard state. We have partial pressures of A and B. We're varying the amounts of A and B, and the way that those different amounts come into play are through their partial pressures. So the more of A there is, the higher its partial pressure will be. The less of B there is, the lower its partial pressure will be. So we have this kind of situation going on here. And now we can define this, or we can define a term. So this, my little rubber tip is finally worn out, so I'm going to take it off here. We can define this reaction quotient. And again, this is something that you've seen in general chemistry. Note, it's not the heat, please. I guess we have 26 letters in the alphabet, and some of them get used more than others. And Q gets more than its share of use. And here it's a reaction quotient Q. And I'll write down a general expression for it, but let's just talk about this particular example. So our Q here, for this example, is this thing that shows up inside of the logarithm. So delta reaction of G at some conditions is the delta reaction G at the standard state plus RT log of Q. And that'll be a general expression for any reaction really. And in particular for any gas phase reaction like we're doing, and we're assuming ideal gases, then that Q is going to be ratios of products of partial pressures to different powers. I wrote down basically the argument of this for that H2 and O2 giving the H2O reaction last time. But so this is general, and this Q is how all the composition of these different gases comes into play. And so and again, channeling Ramesh or whoever taught your general chemistry class, at equilibrium, there are two things that we can note. What is delta? I'll ask you the question because pretty soon I'm going to be doing the asking. What is the reaction Gibbs free energy at equilibrium? This is like one of those Doc Martens questions. Here it is on the final. You either know it or you don't, and if you know what you're doing, you just immediately write it down, but otherwise you're lost, right? So at equilibrium, what is the so this thing, let's think about this, and just let's make sure we're sort of understanding what we're talking about. here we are at some conditions, okay? So there's some pressures of the reactants and there's some partial pressures of the products. And you know, things happen. That's what chemistry, something happens and we start with reactants, let's say, and now we have a mixture of reactants and products. And things keep happening until they stop happening. We call that equilibrium, and that's what I'm talking about here. At equilibrium, we have all the ingredients in this equation, but what is that equal to? RT. It's not log 2 either. It's equal to 0. Okay? Right? So things adjust themselves until the reaction-free energy is 0. That's equilibrium. Because if it wasn't equilibrium, if it wasn't equal to 0, if that thing was not equal to 0, and remember, it's the difference in chemical potentials. Let's go back and remember what that is for our reaction. It's mu B minus mu A, right? And if it wasn't equal to 0, that means the chemical potentials of A and B are not equal. And what can A and B decide to do if they find that situation? Well, like if mu B is higher than mu A, then mu B is going to decrease in amount to lower its chemical potential, because you see, remember these expressions. It depends on the logarithm of the stuff. So you can raise the chemical potential by increasing the partial pressure. You can lower the chemical potential by decreasing the partial pressure. And this is one of these situations where we can't, like if we had tanks of A and B, we could add and subtract A and B from our system. But that's not how it works when it's a chemical reaction. The stoichiometry controls, there's only one variable, right, that's C. And we have this, I'm just reviewing, I suppose, not a bad idea when exams, well, this is G as a function of C, right? And we have a situation like that, and the slope is delta RG. So, like, if delta G of the reaction is negative, then we can go downhill by converting reactant into product. If delta RG is positive, we can decrease the Gibbs free energy of everything by going backwards. Okay, and if we have the just right porridge that Goldilocks favors when having a house invasion, right, of the 3 bears, the poor bears. The bears are always depicted as the bad guys, aren't they? But it's really Goldilocks, if you think about it, right? So anyway, having the just right mixture of A and B to have that slope 0, there's nothing you can do to lower the Gibbs free energy. You're at equilibrium, and that means that delta RG equals 0, okay? So that's one thing that's true at equilibrium. And the other thing is that Q takes on a special value that's equal to K, so that Q becomes the equilibrium constant. Equilibrium constant. That's the definition. Q at equilibrium is K. Okay? So we have 0 equals delta reaction G at standard state plus RT log of K. Sometimes people write, you know, K EQ. That's fine if you like that. You can do that. But K here is good enough for me. I'll just call it K. And so what that means is K is equal to PB over PA at equilibrium. So those are the partial pressures at equilibrium. So there's many ways you can slice and dice these simple facts, I suppose, to ask questions. I could say, I start with 1 mole of A, and then I let it react, and I come to equilibrium. the equilibrium constant is equal to 100. I like these round numbers. Or I could say E squared or something like that. But you know, I could give you a number. Okay, what are the partial pressures of A and B? And that's a problem that you've done before. And, you know, you have a problem like that, a little bit more complicated perhaps. But you know, you can start asking questions about this. Those are the partial pressures at equilibrium. Now we can do other things. We can solve for K, right? So K is this form that shows up all the time in science, is exponential of something. E to the minus, there's usually a minus sign. E to the minus delta sub RG naught over RT. So again, a Chem 1 question. You know, I think I see myself as a nice guy, but you know, I do have a past. And I remember I gave a general chemistry exam once, and you know, I gave them a question where delta G was very negative. Okay, so let's say, so if delta G is, let's say delta G is equal to, let's say it's standard states. Okay, let's say it's standard conditions. So I have 1 atmosphere of everything for my gases. What if delta G is equal to, if the reaction at that condition was equal to 0? What is the equilibrium constant? So let's just like think, we use our common sense. I have a reaction, delta G 0. Does it want to go forward? Does it want to go back? If I'm at standard state, okay, right, I start in standard state, it has no desire to do anything. Like your roommate, like get up and wash the dishes, right? So there's no desire to do anything. What is the equilibrium constant? It's 1, okay? So now if let's say the reaction was delta G was negative. Then what? Okay, so then what is the equilibrium constant? Greater than 1, less than 1, or equal to 1? It's greater than 1. So what does that say? And you know this. It means the reaction wants to go from if it's at standard state, it wants to go to the right. Okay, so it wants to go more to products. It wants more products than you'd have at standard state, less reactants. Likewise, if it's uphill, delta G of the reaction in the standard state was positive, then it wants to go backwards. So what I did to these 400, for a general chemistry student, I gave them a delta G for the reaction, which was really negative. Really, really negative. And if you put it in a calculator, guess what happened? It's too big a number. So, anyway, I was kind of mean of me. I mean, they could write like 10. It could be like E to the 200 would be that's the answer that they should have. But if you put it in a calculator, it didn't work. Anyway, so I think I'm nicer than that now. I promise I won't do that to you. But there's many other things that I could possibly do. Okay, so so like if the equilibrium constant is equal, let's not confuse ourselves though. Let's say I have a reaction. Let's say I had A going to B. Okay. So I have this reaction. Let's do an example. A going to B, and I say K equals 1. And I start with 1 mole of A and 0 moles of B. So the equilibrium constant is equal to 1. Does that mean that nothing happens? No, it doesn't, because it's going to go to getting a half mole of A and a half mole of B. Because then P sub A is going to be X A P, and it's going to be 1/2 P, whatever the pressure is. The pressure, the volume matters and things like that, but there's some pressure. P sub B is going to be 1/2 the total pressure, and P is PA plus PB, And PV equals nRT, right? And so if you need to know the absolute value, you need to know some other stuff. But we don't need that here because PA equilibrium over PB equilibrium is equal to 1. And this fact implies the stuff above. So I'll say this, and I'll say because that's true. Okay? So if I said 10, if K is equal to 10, then you'd have you'd have a ratio of 10 to 1 for the mole fractions. And then you have to figure, you have to figure out what those numbers are. Like, if I said that it was 9, you'd have 9 to 1, right? And then I'd have 0.9 moles of one and 0.1 of the other, because it would have to add up to 1 because of the stoichiometry. Okay. So there's a there's a problem where you can kind of go through this, think this through that I gave to you. Okay. Now, so for this gas phase reaction, there are two, I don't want to say competing. Let's say two collaborating. Let's be positive, right? And not view everything as a battle, right? Social Darwinism. We'll say two collaborating factors, two ingredients that are working together to figure out, how happily this thing will come to equilibrium. We have the enthalpy, and we have the entropy, right? And you know this. Like there's the energetics of the reaction. Are we forming bonds? Are we breaking bonds? If I have A going to B, the example I'm thinking of is like some sort of isomerization reaction. And as you probably know, and if not, you'll see it in P-Chem in future quarters, there's some sort of potential energy surface, right? Like if I take a molecule and I calculate its electronic structure and look at the ground electronic energy of the molecule, and I do that as a function of the geometry. If I twist this bond, this might be more stable than this, and there's some sort of potential energy cost to doing this, okay? And so this might be higher energy than this, and the reason is maybe these guys are repelling each other. They don't like each other, okay? So they're happy to be like this, not so happy to be like that. So here's A and here's B. Delta H, if going from A to B, would be positive, right? So this would be endothermic. I'd have to put heat in to do this. That'll be part of the reaction, right? But then there's also entropy. Now I don't know, like this and this, they probably have a similar entropy. But there's other examples. If I'm breaking a bond, then this is much more entropy than this. And that bond, you might have to put the bond breaking might be endothermic, but then you get entropy. So, in general, these two things work together. So, let's see. So let's say delta RH was greater than 0, for example. Right? Well, let me actually make sure. Look, I can erase this blue line. That's kind of interesting. But then it comes back. You learn something new every day, don't you? Let's say it takes something like A going to 2B. So that could be like breaking a molecule into two pieces. Let's just say that's what we're doing here. And let's say delta reaction H is greater than 0 because the bond, A is equal to B2 or something like that, you could say. So energetically, we expect mostly A, right? but there is an entropy, and let's say these are gases, G, G. You know, we have this delta S of mixing, right, which is minus NR x sub A log x sub A plus x sub B log x sub B. And you know x sub A plus x sub B equals 1. X sub A, let's say,
what does entropy
entropical. There is an, but there is an. What am I saying here? Let me. There is an entropic, entropic factor. Well, factors mean a multiplicative factor. Let's say an entropic contribution. Yeah, let me not get too in the weeds on it. But there's another term, right? And if we think about this, you know, if we had let's say we had all A, right? Then that delta S mix is going to be equal to 0, because I'll have a both 1 log 1 plus 0 log 0. And the 1 log 1, I think everybody's happy with, 1 times 0. But the 0 log 0 is like 0 times minus infinity. And we have to think about that, but I think I said other, you know, people have thought about that, and we're not going to prove it or anything, unless, well, maybe we should, but let's not do it. But a 0 log 0 is equal to 0, okay? So when you take the limit. So there's no entropy of mixing. Like if you have having all A to start with, you get no entropic contribution. But if I take the A and convert it to B, now I've got mole fractions that are less than 1, and I get a positive because there's a minus sign out front, an entropy of mixing. Now to actually calculate it, we'd have to be careful, because that N out front, everything depends on the degree of advancement, right? And so for every mole of A I lose, how many moles of B do I make? 2, okay? So you have to do the bookkeeping right. You have to keep track of where you are in this coupled stoichiometric mix of A and B. You have to figure out what your mole fractions are. You have to figure out what your partial pressures are if it's a gas reaction. But the idea here, I hope is clear. So if I have this, let me just remind you. Well, let me not even draw that. I think it's probably clear enough. So let's leave it at that. Now we need to mention something that I skipped, but I probably should have mentioned it a little earlier. But we can mention it now. There's something called the activity, and this is an important quantity in physical chemistry. It's like a mole fraction with reality. Let's not say that. That's kind of it's a cryptic way of saying something. For non-ideal, for ideal and for non-ideal systems. Okay, so we're talking about the ideal gas, and I'll say it's not really the mole fraction. It's like the mole fraction. So if I'm talking about an ideal gas like we have been, and I had the mole fractions XA log XA and XB log XB, fine. I mean, the mole fraction is this activity. But if you start getting into real systems, you'll see this activity uh, uh, used. Okay, so recall uh, we had and I'm thinking now for this is for a solution. Uh, uh, yeah, let's just say it's for a solution. So we had this pure. This is the chemical potential of the pure substance. And remember, that would have been like A liquid and A vapor in equilibrium, and there's nothing else in there. Just the vapor. There's no air in there. Pure liquid, pure vapor. There's an equilibrium between the liquid and the vapor, and if it's pure liquid, then we had equilibrium, right? There's a delta, a change in chemical potential that is zero, going from the liquid to the vapor. So liquid and vapor chemical potentials are equal to each other, and the chemical potential of the liquid is equal to chemical potential of the vapor, and that would be when the vapor pressure of the pure substance is equal to the vapor pressure of the pure substance. So this would be like the chemical potential of the liquid be equal to the vapor would be equal to the chemical potential of the liquid. So let me, this is the vapor and this is the liquid, pure substance. But the vapor has another term, which is that second term, which adjusts for the fact that maybe it's not a pure substance. So, like if I mixed A and B, then the vapor, the chemical potentials would be lowered because the partial pressures would be less than the pure substance. And remember Raoult's law. We had the partial pressure was the mole fraction times the pure substance, and we did some discussion about that. Now, for non-ideal solutions, then we generalize mole fractions to these activities. And so, so A sub j is the activity of species J. And A sub j is sort of approximately equal to X sub j. It's filling in for the mole fraction. And the reason they do this, I never liked activities much. They're okay I can tolerate them now. I used to hate olives. They're okay actually, because back in the 70s or the 60s, the olives you got were pretty bad. They were in these cans. But I've gotten used to them, and I've also gotten used to the activity. And the reason that it's used is because we can just keep using the same expression. So this is basically always true, and I put that in quotes, because you never know. But so we want to be able to use a formula that looked like the one we had before. And that was for the ideal gas. With Raoult's law working, we had mu sub j equals mu sub j star plus RT log X sub j, right? Because it was P sub A over P. Anyway, we had this kind of thing going. So we want to always have a similar formula, even if we're talking about things that are not ideal gases. And especially like if you go into doing chemical reactions for, I mean, systems that are actually interesting. So you have like a solution, you've got some non-volatile things in there, you've got some volatile things in there, non-ideal solutions, it's a lot of salt ions in solution, all the interesting things that physical chemists study when they're, get out of a class like this and start doing, studying the real world as it truly is, not as it is with ideal gases. Then their activities are used a lot, and but this is what you see. This is the expression, and we're not going to say too much about this. Just pretty much what I'm saying here, but there's something which you will probably run into, and probably you did even already somewhere. There's something called the activity coefficient. And usually it's like gamma sub j. Gamma has been set aside for activity coefficients. And what it is, this is bad grammar, so never write a paper that says what it is. But what it is the fudge factor that you have to multiply the mole fraction by to make it true. Okay, so it's that number that you just look up in like if you're doing reactions in some ionic solution, and you just go and look up in a table what the activity coefficients of things are, and then you can use the mole fractions, because the mole fractions are pretty easy to calculate, because you know how much moles you're mixing, the total number of moles, you know the stoichiometry, this and that, and then you just want to be be able to do your thermodynamics, and they have this expression here. And so this activity coefficient goes to 1 as systems go to ideal conditions. And so, it often, like let's say such as xj goes to 1. So it's all rigged up, so like if I have the pure solution, the pure substance, then this thing here, oops, I can circle it. That thing here is the chemical potential of pure stuff, and as xj goes to 1, then that it just becomes true. And if it's a very little, just a small trace of anything else in there, it's basically the pure stuff. It's going to act ideally. But if you have like equal portions, then non-idealities will come into play. And it's also true if xj goes to 0. Okay, so if you have pure substances, then the pure substance properties come back. But I'm not going to say anything else about it. Let's skip the details. But let's now pretend like we know all about it, and so I can go back now. That's it. Go back to the thermo. And I can write down my delta G for the reaction is, again, let's review. We have the sum of the stoichiometrically weighted. Remember, the n's are positive and negative depending upon if you're a product or reactant. And we go through everything, and so we have our sum of j, nu sub j, mu sub j, maybe a standard condition plus RT log A sub j. Now look, there's our activities. I've just replaced things with the activities. Oops, no. I've just made a common mathematical error. Let's not do that. So I'm doing this because I want to. Why am I doing this? That's a good, always a good question. Probably you asked that. I want to come up with the expression for like the equilibrium constant, the reaction quotient, but that you would use no matter what chemical reaction you're talking about, whether it's something the organic chemist would do or the gas phase reaction like we would do. And for gas phase reactions, those activities would be partial pressure divided by P naught, right? But now there is, which could be a mole fraction, but here it's an activity. And so we're doing this in total generality. There's always a standard state change in Gibbs free energy. We have our RT. I have my sum, and now I'm doing a little bit of mathematical algebra. Remember, like x log y is log of y to the x. So I put those stoichiometric coefficients into the logarithm, and then the sum of logs is equal to the product, the sum of the logs of things is the log of the product of things. Okay, so let me remind you of that. So x log y equals log y to the x, and log x plus log y is log xy. So we use those two things. The first one we used here, and the second one we're going to use down here. And have you seen that capital pi thing used before? Okay, you know, so like sigma sub j, a sub j is a1 plus a2 plus a3 plus dot dot dot, right? This is the sum. You know, and some mathematician invented this notation. I can't remember who. I probably never knew who. But yeah, and you know, you guys have had to put up with that, you know, for years. But they didn't stop there. You know, they came up with this notation, which is a1 times a2 times a3 times dot dot dot. So the product. So just like sigma summed over j is the sum of the indexed things that are in the sum, and so that, and you know, the log of log pi sub j x sub j equals sigma sub j log of x sub j. Okay. You know, it's math, isn't it? But that, you know, that's true as long as I didn't make a mistake. The log of the product is the sum of the things. And so what this has allowed one to do, let me write it down here. Is to have everything in one, like all packaged up. It's like you've wrapped your holiday presents, okay? Everything is, you bought 10 things on Amazon and they put it all in one box and shipped it to you to save, you know, decrease your carbon footprint. And so this thing here, Q, is really the product. Basically, that's the punchline. I've made something that you thought you knew what it was to be maybe more complicated than it has to be. But this is like, you know, a reactant 1 to the new reactant 1, a reactant 2 to the new reactant 2, dot dot dot. And I'm sorry, these are products. Products are upstairs. And I put the reactants downstairs, And this is what you like, what is it? Ka, is H plus A minus over this. I apologize if this is triggering, from Chem 1, but you did problems like this. The acid dissociation constant is, for acetic acid, is this 10 to the minus something, right? Calculate the pH of the solution. And remember, HA is a reactant, but it dissociates when you put it in water, and the H plus and the A minus are products, right? So you have those products upstairs, you had the reactant downstairs, and then you had a constant, and you worked it all out. And because you don't like solving quadratic equations, you made an approximation. There's all that stuff. Brings it all back, right? And so in our business, we have those n's which are positive and negative. And remember, the stoichiometry are positive for the products, so they're just raised to like a something squared, something cubed, something to the first power, whatever. But the reactants are negative. So then you have like HA to the minus 1, okay? Because the nu can be minus 1 if it's a reactant. But you don't like that. And I don't like it so much either. So here it is in the denominator. But that's why I put absolute values there, because they're really not positive. This is the thing. Okay? So it's a nice clean way. If you're comfortable with it, then it's a clean way to write it. And we can go from there. And so let's look at an example in our remaining 5 minutes, I suppose. This is from the book. There's something called a brief illustration that's in the book, and it's 6A.3. Okay. I don't know. I don't like this. I don't like the numbering situation in this book at all. Anyway, we have this reaction. And let's just go through it and just. I think it's probably clear, but let me belabor this. And so let's identify our stoichiometric coefficients of our products, right? So here's products. And our reactants are here. And if our A sub j's are equal to X sub j, we could write our Q. So this is like if it's an ideal system, which our Q is the product over J, A sub j to the nu sub j. Oops. A sub j to the nu sub j, which then can be the product over J, A sub j to the X sub j. Whoops, no. There's two possibilities what it could be, and I got it mixed up. There we go. X sub j to the nu sub j. And now we have to think a little bit, right? So I have a reaction. Well, so I have PA equals X sub A P. PB equals X sub B P. And P is PA plus PB plus PC plus P sub D, right? That's the total pressure. And if I know the mole fractions, and I know the total pressure, then I can get ABCD partial pressures that way. And my Q is going to be x sub c to the nu sub c. Well, let me write it like this. X sub a to the nu sub a, x sub b to the nu sub b, x sub c to the nu sub c, x sub d to the nu sub d. And if I work that out, I've got x sub c, what is c? To the first power, x sub d to the squared, and in the denominator, now we're getting somewhere, right? We're actually seeing what these things are, squared, and x sub b cubed. And we're good because this thing is dimensionless, as it's supposed to be.